Hi kids, welcome back. This is Chapter 7, Higher Horizons, 1955 to 1965, the decade of rockets and jets, Part 1. Let's talk about rocket development after World War II. As the war was coming to an end, Wernher von Braun and his team had a decision to make. Did they want to be captured by the Soviet Union or by the United States? They decided wisely. They decided to be captured by the US. But the Red Army was much closer to where they were in Peenemünde in northeastern Germany. So they had to borrow some vehicles and use some fake paperwork and headed west. And they finally wound up finding the Americans and surrendered to them. On the way, von Braun managed to break his arm, and that's why you see in all the classic photos of him surrendering and having a smoke with the Americans is his arm in a cast. That's the sort of classic surrender picture. After World War II, Operation Paperclip brought von Braun and his team to work in the United States to develop the U.S. rocket program. So despite the National Security Act of 1947, which created my beloved Air Force, it was also supposed to unify the military services under one Secretary of Defense. It was also supposed to streamline things. Well, that didn't quite work out. Inter-service rivalry continued, especially in this new field of rockets and missiles. So now it wasn't just the Army fighting the Navy. Now the new U.S. Air Force also was in on the act, and they wanted to get in on this missile business. So the U.S. Air Force case for being in charge of missiles was that we do long-range bombardment. The Air Force prosecuted the strategic bombing campaigns against Germany and Japan during World War II with their B-17s, B-24s, and B-29s. They dropped the two big ones on Hiroshima and Nagasaki. And now they had nuclear weapons and the B-50, the B-36, the new swept-wing jet B-47, and soon the new B-52. So because of this long-range strategic bombardment experience, the Air Force thought they should take the lead in missile development and operations. Well, the Navy pointed out that ships and even submarines now could carry missiles and could carry them anywhere on the globe, so they should get missiles. Finally, the Army noted that missiles and rockets are just long-range artillery, and the Army has always been in the artillery business. Fortunately for the new U.S. Air Force, the Army Air Forces, before separation, had initiated long-range missile development even before the end of World War II. So this gave the Air Force a big advantage. The Air Force began by developing a series of long-range cruise missiles, and these were pretty big cruise missiles. Compared to today's cruise missiles, they were humongous. So the first-generation nuclear warheads were large. So like the original 21-kiloton Fat Man A-bomb, which was replaced by the Mark IV of 31 kilotons, they were still huge weapons that weighed like 10,000 pounds or more. And so therefore the cruise missiles and airplanes have to be large enough to carry them. The Air Force developed a whole series of these large cruise missiles in the 1950s. The first was the Matador. It had a 650 mile-per-hour speed, a range of between 250 and 620 miles, and had the early W5 50-kiloton warhead. It was operational from 1952 to 1962. The Mace, which was a follow-on weapon, was also flying at 650 miles an hour, but its range was 1,400 nautical miles, and it had the larger W28 20-kiloton to 1.4 megaton weapon. It was operational from 1959 all the way up to 1970. The Snark was a 650 mile an hour cruise missile with a 5,500 mile range, and it used the new W39 thermonuclear 3.8 megaton warhead. It was only operational from 1959 to 1961. The ultimate cruise missile in the 50s was going to be the Navajo. This was going to operate and cruise at Mach 3 for 5,500 miles. It had testing, but it never was operational. It was canceled in 1957 as the new intercontinental ballistic missiles started to become practical. The Navy was also experimenting with slightly smaller cruise missiles that they could fire from ships and submarines. These were new missiles like the Regulus 1 and the Regulus 2. Regulus 1 cruised at 0.85 Mach for 500 miles and had the W5 50-kiloton warhead. It was operational with the Navy from 1955 to 1964. Irregulus II was a Mach 2 vehicle, which was going to go 1,200 nautical miles and had the W-27 thermonuclear warhead of 1.5 megatons. It was canceled in 1958 before becoming operational as the new Polaris intermediate and later intercontinental range ballistic missiles became practical. So while cruise missiles were being developed by the Air Force and the Navy, the Air Force was also developing larger and larger intermediate range ballistic missiles and intercontinental ballistic missiles. So the Intermediate Range Ballistic Missile, or IRBM, or the Intercontinental Ballistic Missile, ICBM. The earliest of these missiles for the Air Force were the Thor and the Atlas. The U.S. Army's missile development operations were originally based at Fort Bliss in El Paso, Texas. Just to the north of El Paso in New Mexico was the White Sands Missile Range, where a lot of missile testing did and still does take place. Von Braun's team settled at Fort Bliss in 1945 and started launching the numerous V-2s that had been captured at the end of the war. One of the things that von Braun's team developed the expertise in was firing multi-stage rockets. They were using the V-2 as a booster, and then they would make smaller sounding rockets like the WAC Corporal on top of that, which would then continue flying after the V-2 booster had expended. So this was called the Bumper WAC series, and this was where they gained experience using staged rockets. It should be noted at this point that even though Robert Goddard, who we know built and flew the first liquid-fueled rocket in the world on March 16th of 1926, by this time his work had been completely eclipsed by von Braun and his team. So at the end of World War II, Goddard was understood as the recognized pioneer of liquid-fueled rockets, but that it was von Braun and his team who were considered the real fathers of the U.S. rocket, missile, and space program. Virtually every U.S. rocket today is a direct descendant of von Braun's work. Von Braun's work led the Army to its first operational missile, the Redstone. The Redstone was named after the Army's Redstone Arsenal, which is located in Huntsville, Alabama. Von Braun and his team moved from Fort Bliss to the Redstone Arsenal in 1950, where they developed the Redstone missile. The Redstone was a short-range ballistic missile with a range of only 175 miles. It carried the 3.5 megaton W-39 thermonuclear warhead, which weighed over 6,000 pounds with its re-entry vehicle. Remember, the V-2 had a slightly longer range, but it only carried a 2,000-pound conventional warhead. The Redstone was operational from 1958 to 1964. The Army and the Navy actually cooperated on the next generation missile, which was called the Jupiter. However, since the Jupiter used liquid fuels, the Navy feared fuel leaks and explosions aboard ship. The Navy had tested launching liquid-fueled rockets from a ship on September 6, 1947 during Operation Sandy, when they launched a V-2 from the USS Midway aircraft carrier. This marked the first launch of a large rocket and the only launch of a V-2 from a ship at sea. In 1956, the Navy finally opted to switch to a solid fuel rocket for the future use aboard submarines and ships and left the Jupiter program to the Air Force, and they continued on with their solid fuel program. The Navy did retain the guidance package developed for the Jupiter missile for their new solid-fueled Polaris missile. Originally, the Polaris missiles were slated to be based on surface ships, but with the success of the USS Nautilus in 1954, the world's first nuclear-powered submarine, nuclear submarines were seen as being a much better platform for hiding ballistic missiles from the Soviets. With their ability to cruise virtually indefinitely underwater, obviously that was the way to hide your missiles. The first ballistic missile carrying submarine was originally laid down in 1958 as a skipjack-class attack submarine. It was going to be the USS Scorpion SSN 589. The Scorpion instead had a 130-foot-long ballistic missile section added amidships, which would carry 16 of these Polaris missiles, and it then became the USS George Washington, SSBN 598, and commissioned in December of 1959. In a weird connection, a later Skipjack-class submarine was also given the name USS Scorpion and the hull number 589. She was lost at sea with all hands in 1968. This made the Scorpion only the second and currently the last U.S. submarine ever to be lost, and only one of two U.S. nuclear-powered vessels to be lost at sea, both submarines, the first being USS Thresher in 1963. So the Navy's Polaris A-1 missile being developed out of the Jupiter program was only the start of the Polaris, Poseidon, Trident family of missiles. These were all submarine-launched ballistic missiles, and they generated also 6 generations of fleet ballistic missile submarines to launch them from.
Polaris missiles arrive at Cape Canaveral for their first test firings from the nuclear submarine expressly designed for the job, USS George Washington. The tests are a stirring climax to a 4-year program to mate the nuclear submarine and the intermediate-range ballistic missile. Now the sub's missile hatches are cleared and ready. They'll house the 28-foot two-stage rockets until the moment when mighty gusts of compressed air will shoot the Polaris from under the sea to the surface and ignition. Every stage of the loading and the cruise to the firing area about 30 miles off Cape Canaveral is under detailed scrutiny of a battery of test instruments. The George Washington goes down some 50 to 60 feet below the surface, and the time for launching is at hand. The first missile, after a startling off-angle emergence, corrects itself and soars downrange 1,100 miles to its target with remarkable accuracy. A few hours later, the second Polaris is fired. Another successful shot, an achievement of major strategic importance for America's defense.
The Polaris series was the Polaris A1, A2, and A3, each getting larger. Then the larger diameter Poseidon C3 and C4. And finally today's even larger Trident D5 missile. The original class of ballistic missile submarines was the George Washington class, followed by the Ethan Allen class, the Lafayette class, the James Madison class, the Ben Franklin class, and today's Ohio class, which instead of 16 carries 24 of the Trident D5 missiles. Remember back to the 1930s when Curtis LeMay led 3 B-17s out to intercept the wrecks, and then the War Department restricted U.S. Army Air Corps aircraft to stay within 100 miles of the coast to protect the Navy? Well, in 1956, the DoD did something similar. They split up missile responsibilities between the Army and the Navy. They limited the U.S. Army to missiles with ranges of less than 200 miles, and the Air Force got missiles with ranges of more than 200 miles. Now a short detour into nuclear weapons. In July of 1945, the U.S. set off its first nuclear weapon at the Trinity site in New Mexico. So from July of 1945 through 1949, the U.S. had the nuclear monopoly. We were the only country in the world that had nuclear weapons. However, once the Soviet Union demonstrated on 29 August 1949 that they too had the bomb, the nuclear arms race began. Bigger was definitely better in the boom department, but smaller was better in both the size and weight department. Smaller warheads meant you could carry a more smaller aircraft or missiles, or later on you could carry more warheads per missile, or that same missile could carry a single warhead farther. So smaller was definitely better. The Little Boy and Fat Man weapons that were first used in anger on Hiroshima and Nagasaki both weighed right around 10,000 pounds. Little Boy yielded 15 kilotons of TNT and Fat Man 21 kilotons. Later, our operational weapons, the Mark IV and Mark VI atomic bombs, were essentially just modified and more producible and safer versions of the Fat Man. They still weighed between 8 and 10,000 pounds, but now they yielded between 31 to 160 kilotons. You still needed a large airplane to carry these things. The really big deal was the development of hydrogen bombs, or thermonuclear weapons. The U.S. tested the world's first H-bomb on the 1st of November, 1952, on an island in the Inuiatak Atoll in the Pacific. The test was codenamed Ivy Mike, and the Mike weapon weighed 82 tons. That's because it wasn't really a bomb. As they said, it was an installation. The Mike device was essentially a building that resembled a factory, rather than a usable weapon. The factory was needed to supply the liquid deuterium gas and other liquid gases needed to keep the weapon cold. It was reported that a Soviet engineer derisively referred to the Mike device as a thermonuclear installation. So it's not portable. This was like many airplanes, like the X-planes, it was a proof of concept. We just wanted to see if the basic idea would work. The test proved that the basic design of the H-bomb, the Teller-Ulam design, was using fission, which led to fusion and then still more fission, did work, and the Mike device yielded 10.4 megatons. The key to a smaller and therefore more deliverable H-bomb was the use of a solid fuel. They used solid lithium-6 rather than a liquid lithium deuteride fuel, which was used to fuse in the fusion reaction. This was attempted during Operation Castle Bravo. This was the test of our solid-fueled nuclear weapon, H-bomb. The 1954 device on March 1st was called the Shrimp, because it was much smaller than the Ivy Mike device. And this was the most powerful nuclear bomb that we'd ever detonated. And it was the first to use the solid lithium deuteride fuel. The Castle Bravo yield was expected to be about 6 megatons, a little bit smaller than the Ivy Mike device. However, due to the unforeseen additional reactions involving lithium-7, in addition to the lithium-6, they didn't understand the physics quite right. The Castle Bravo test yielded 15 megatons, 2.5 times its expected yield. Oops. This led to some severe problems where crews that were supposedly at a safe distance were now actually in danger. They had to remain in bunkers a couple miles away from the blast site. And there was a Japanese fishing vessel which was outside the exclusion zone, but was still covered with radioactive debris, and a number of the crew were seriously injured with radiation poisoning. Based on the design of the Castle Bravo device proving the solid fuel worked, the first operational H-bomb in the arsenal, the Mark 17, was still so large, weighing in at 42,000 pounds, that only the gigantic B-36 bomber could carry it, and it could only carry one. However, as the warheads got smaller, smaller aircraft and smaller missiles could carry them, or could carry more than one warhead. Later on, warheads like the 9-megaton W-53 were carried on the later Titan II missiles, and warheads like the W-78, which weighed only about 800 pounds, were carried on the Minuteman III ICBM. The Minuteman I carried one RV, one W-78, and the Minuteman III could carry 3 of the 350 kiloton warheads. And these 3 warheads were carried on the Mark 12 reentry vehicle, and each warhead could be independently targeted. Thus, they became multiple, independently targeted reentry vehicles, or MIRVs. In an odd attempt at humor, the conical shape of the W-78 and its reentry vehicle has been referred to as the nuclear dunce cap. Today, small cruise missiles can carry the W-80 warhead or similar warheads, which only weigh about 290 pounds and can select dial a yield from between 5 kilotons to 150 kilotons. So smaller, lighter warheads made for smaller missiles or larger missiles that could carry multiple warheads or carry them much farther. End of the nuclear detour. In addition to the cruise missiles, the U.S. developed a series of larger and longer range missiles, ICBMs, in the late 50s. In 1957, Douglas built the single-stage Thor with a range of about 1,750 miles. That would be an intermediate range ballistic missile. And Convair, in 1958, built the stage-and-a-half Atlas missile with a range of up to 9,000 miles, a true intercontinental ballistic missile. So what is a stage-and-a-half rocket? Well, the Atlas had 3 engines at launch, and all 3 were fed from the same fuel and oxidizer tanks in that main stage. After some time, 2 of the engines would shut down and drop off, sort of the half stage, and the remaining half stage would continue up with the single center engine. In 1959, Martin Marietta built the 2-stage Titan I missile with a range of 6,100 miles. It carried the Avco Mark IV reentry vehicle containing a W-38 thermonuclear weapon with a yield of 3.75 megatons. Later, the Titan II was developed and deployed with the larger W-53 warhead yielding 9 megatons. 54 of these Titan IIs remained on alert from 1963 to 1986, and we kept it so long because the 9 megaton warhead was the largest in the arsenal for a long time. That was our bunker buster. While the Air Force was continuing to build the liquid-fueled ICBMs, they were keeping an eye on the Navy and their solid-fueled Polaris missile. In addition to being safer, no liquid fuels to handle, it also promised quicker launches. You could just launch it in instants. In 1957, the Air Force contracted with Boeing to produce a solid-fueled ICBM, which would become the Minuteman family of missiles, the Minuteman I, II, and III series. As the 1950s came to a close, the DoD announced the integration of these new long-range ICBMs into the U.S. Air Force inventory, replacing a large number of bombers, manned bombers. As long-range land-based ICBMs and submarine-launched ballistic missiles joined the manned bombers on 24-hour alert, the nuclear triad was created in the early 60s. Land-based manned bombers, land-based ICBMs, and sea-based missiles on submarines. In 1961, the Single Integrated Operational Plan, or SIOP, was introduced. This was the United States General Plan for Nuclear War from 1961 to 2003. The SIOP gave the President a range of targeting options and described the launch procedures and the target set against which nuclear weapons would be launched. The plan integrated the capabilities of the nuclear triad of strategic bombers, land-based intercontinental ballistic missiles, submarine-based ballistic missiles. By the mid-1950s, the growing lift capability of military boosters made sending scientific payloads into the upper atmosphere routine, and placing them into orbit a distinct possibility. Sounding rockets like the Araby and the Viking could reach altitudes of 100 to 200 miles above the Earth's surface. Unfortunately, they did not have the energy to accelerate to an orbital velocity of about 17,500 miles per hour. Which brings us to the International Geophysical Year, or IGY. This is from the NASA webpage. Following a suggestion by National Academy of Sciences member Lloyd Berkner, the International Council of Scientific Unions in 1952 proposed a comprehensive series of global geophysical activities to span the period July 1957 to December 1958. The International Geophysical Year, as it was called, was timed to coincide with the high point of the 11-year cycle of sunspot activity. In March of 1953, the National Academy of Sciences appointed a U.S. National Committee to oversee U.S. participation in the International Geophysical Year. The U.S. program included investigations of aurora and air glow, cosmic rays, geomagnetism, glaciology, gravity, the ionosphere, determinations of longitude and latitude, meteorology, oceanography, seismology, all sorts of ologies, solar activity, and the upper atmosphere. In connection with upper atmosphere research, the U.S. undertook to develop an orbiting satellite program. It was from the International Geophysical Year rocket and satellite research that the U.S. developed its space program with the advice of the National Academy of Sciences Space Science Board. As part of the International Geophysical Year, the U.S. ended up launching 210 sounding rockets, and the Soviet Union launched 125. These are, again, rockets that just go up and come right back down, not in orbit. But as early as 1955, the U.S. was planning to launch a satellite into space as part of International Geophysical Year, and a committee was formed to choose a booster. But which booster should they choose? Should they choose the Atlas? The Army Ballistic Missile Agency said no, it's not tested. How about the Redstone? The Viking. It would need a larger first stage, a new second stage, and a new third stage in order to reach orbit. The Army's Jupiter C, based on the Redstone, seemed to have it all, and von Braun and his team were prepared to add an upper stage to the Jupiter and launch. But no. The committee picked the developmental and still untested Viking booster. Their reasoning was that the new Viking booster had been designed from the start as a civilian booster, not a military booster. This would look good to the U.S., because we weren't militarizing space, and the committee didn't want to interrupt military booster production, so Viking. In 1955, the new program was placed under Navy supervision as Project Vanguard. In October of 1957, the first stage of Project Vanguard was fired successfully, and then, in December of 1957, the first all-up three-stage Vanguard rocket was tested, and it failed spectacularly. Let's watch. And to add insult to injury, anyone? Anyone? Bueller? Yeah, the point was moot. On the 4th of October 1957, the Soviet Union had placed the world's first artificial satellite, Sputnik 1, into orbit. Sputnik, by the way, means traveler in Russian. To quote the French pilot, Léon Delagrange, who after witnessing Wilbur Wright's first flight in France on 8th of August 1908 was heard to mutter, "We are beaten," that's pretty much the way that we felt in the West, especially the United States. And if it wasn't embarrassing enough, the next month the Soviet placed the first living creature into space, Laika the space dog. However, those commie bastards had no way to return Laika to Earth. She spent her last hours alone and died from heat stress. No red-blooded American would send a dog into space to a certain death. None of us. In a few years, the U.S., we would even send 2 feces-throwing space chimps into orbit and bring them back alive. End of rant. Back to boosters. So what to do about the Soviet space coup? The United States was freaking out. This new red moon was orbiting the U.S. every day. Amateur radio operators could listen to it beep and mock us. The U.S. needed to respond with a successful launch, and fast. Who can we turn to?
Today, a new moon is in the sky, a 23-inch metal sphere placed in orbit by a Russian rocket.
The reaction was one of astonishment and concern, for it was now known that a potential enemy was at least temporarily ahead in developing means for space travel.
President Eisenhower reassures the nation that Russia's success with the first satellite does not indicate a serious lag in American rocket research.
The morning of November 8, 1957, at Huntsville, Alabama. A sudden meeting has been called by General John B. Medeiros, Commanding General of the Army Ballistic Missile Agency.
I promised the Secretary of the Army that we would be ready in 90 days or less.
All at once, Americans were interested in the oncoming age of space. And with the curiosity came a mounting, swelling demand to get a satellite into the air on the double. But there were disappointments.
Another setback for the United States, a loss of thrust and fall back to Earth in split second.
But meanwhile, far across the country at the Jet Propulsion Laboratory, a sprawling 80-acre research and development complex in Pasadena, California, scientists and engineers were racing toward the same deadline: 90 days to put a satellite into orbit.
The Army is requesting the Jet Propulsion Laboratory to provide the following programs. First, the additional high-speed propulsion systems required. Second, the orbiting missile or satellite. And third, the necessary instrumentation to record and transmit the scientific data assigned to this experiment.
This assembly, which is the actual payload for the satellite, contains both transmitters, the necessary circuits for the impact microphone, which will detect the collisions with meteorite particles, and a Geiger counter to measure cosmic ray intensity.
The government turned to Wernher von Braun and his team. After initially being rejected to launch the vehicle into space, von Braun and his team had continued to work on the Jupiter by giving it orbital capability. How did they do this? They did this under the guise of re-entry vehicle research, or RV research. An ICBM, when it launches, may fly many hundreds of miles outside the atmosphere, and as it comes back, it re-enters the atmosphere, usually at very high speeds, many times the speed of sound, supersonic and even hypersonic speeds. Later ICBMs came back on the order of Mach 20. So in order for an ICBM to be accurate, to hit its target, the flight characteristics and aerodynamics of these RVs must be well understood as they travel at hypersonic speeds through the atmosphere. And how do you determine this? Testing. And how do you test? You have to have a rocket that can send a payload high enough to bring it back at those high speeds. So they did that. Von Braun launched a three-stage Jupiter C with an inert fourth stage. It had no propellant on it, and they put the RV on top of that. Had this fourth stage been live when they launched it, they determined that it would have had enough energy to put the payload into orbit. So, when the Secretary of Defense came calling after Sputnik, von Braun was ready. 4 weeks after the launch of Sputnik, the Secretary of Defense gave the go-ahead for the Army Ballistic Missile Agency to launch an artificial satellite using the Jupiter C. Authorization for 2 launches came on 8 November 1957. Not even 2 months later, on the 31st of January of 1958, the Army Ballistic Missile Agency's Jupiter C placed Explorer 1 into orbit, our first satellite.
Wrong, with catastrophic results. But all that can be done to assure perfection has been done. The moment is at hand. The countdown reaches 0.
Fire command, fire command.
Some 3 minutes later, Explorer is in orbit, broadcasting to the world its coded scientific data. This close-up of the United States edition of Sputnik was made at a press conference with leaders of the scientific teams, Dr. Wernher von Braun, Dr. James Van Allen, and Dr. William Pickering, a 3-way collaboration between private industry, academic science, and the military. Cosmic ray intensity, meteor impact, solar radiation. These are the dry facts that will help carry man ever farther into the age of space.
The Jupiter C booster was then named Juno for space launches. Later, on the 29th of July, 1958, the NACA, the National Advisory Committee for Aeronautics, adds space to its mission, and the National Aeronautics and Space Act created the National Aeronautics and Space Administration. NASA is born. Now, unlike Sputnik 1, which just beeped, literally it just beeped, listen. That's it just beeps. The Explorer 1, our first satellite, actually had a scientific payload aboard it, developed by Dr. James Van Allen. And what he discovered is now called the Van Allen radiation belts, and they're found around the Earth at different altitudes. So this was a major discovery and was made possible by an actual scientific payload on our satellite, unlike just a little radio transmitter for those commies, the ones who killed the dog. Many scientific payloads were launched over the next few years in an explosion of research in space. The first missions were called Explorer, and they orbited both the Earth and the Moon. Well, some of them crashed into the Moon. Pioneer missions were sent to Venus and some of the other planets. Ranger missions were sent to photograph the Moon. And Surveyor missions were even sent to soft land on the Moon and take photographs to prepare for the Apollo program. Soon, placing satellites in orbit became almost routine, and a variety of vehicles were launched and placed into orbit. There was the Transit satellite. Transit was a Navy navigation satellite and precursor to the current GPS constellation. There was TIROS, Television Infrared Observation System, for weather forecasting. These crude weather maps of the Earth from space may look pretty crude today, but they were a revelation in forecasting. The Orbiting Solar Observatory went in orbit around the Sun, not the Earth, to observe the Sun. We still have vehicles orbiting and observing the Sun. Telstar, the first communications satellite, also spawned a pop song by the Tornadoes called Telstar. Let's listen. Yeah, it's kind of weird, but it was the 60s, man. Later, low Earth orbiting and then later geostationary orbiting satellites were used to send TV signals around the world. So the Olympics and other international events could be watched live via satellite. Midas satellites were developed to watch for Soviet ICBM launches. They would detect the hot plume of the boosters as they launched their rockets, give us a warning of an attack. There was Vela satellites to watch for nuclear detonations around the world to see who was setting off nukes. Nuclear weapons have a very distinct pattern across various spectra, which the Vela watched for. And finally, there was the Corona series, classified photo reconnaissance satellites, which took film images and then dropped the film capsule back to Earth, where they were picked up by parachute in midair by special aircraft or lost in the Pacific. Well, that's the end of part 1. We hope you tune in next time, whenever I get around to making it, to the part 2 of chapter 7. We'll see you then.